Okay, so I will do the 7.3.1. So I give you some examples first. So we have some quadric in our I 0 plus 1. So this is a hemisphere in this space SI0. So let's consider affine space with these corners here. So we of course this will have a from the vector space of dimension I0 plus 2. So we have these corners, and upper hemisphere can be defined by this equation. So this is a affine space, and you can find the standard quadric like this given by this equation. And the group of orthogonal map acts on this any of these I0. So these are ones acting on the I0 to 1 to I0 coordinate. Okay. So it will act on these these are constant, and they will act on there. And so the group of matrices of this form will act on this quadric. So V is of course in this uh, I0 dimensional vector space. Okay. So you can do explicit computation and show that it acts like that. And this is actually transitive action, and it is actually isomorphic to Ri0. Okay, because this is just so this is just a group of vectors actually isomorphic to these group of vectors. So the group of affine transformation that acts on the quadric is exactly this group. So if you can think of this as so sitting on some quadric that project to the I0 dimensional space given in here by saying that x I0 plus 1 is some is 0. Okay, so it's a quadric sitting over this plane. So you have I0 dimension xi0 plus 1 being constant and 0, and then there is a quadric sitting over there. You can think of it like this. So the equation is like this. You can of course drop this. I mean, you can set this to be 1, and then it will be a quadric like that. And so affine transformation that acts on this is exactly the Lie group and this group OI0. Okay, of course that acts on here. Okay, so this group is transitive and stabilizes always conjugate to this group. And so this group is like you can write it n prime v0 for v in I0. So this is unipotent cost group, and then you can give a coordinate. So for the some standard vector, you can do this, and then these are always you can write it like this. So the example of generalized joint, and so this is a joint and not yet quasi joint. Is so let's take a totally geodesic Rn with the Pn labeled U1 in the universal cover. Um, and then there's a Pn vertex B1 and E2 with a Pn labeled U2, which is horospherical one with a vertex B2. Okay. So we look at these two things, which is in n minus I 0 minus 1 dimensional. And then there's I plus 1 dimensional. So they are not, I mean, they're not disjoint, so they might intersect at B1 equal to B2. So we can just set B1 equal to B2 and then make the intersection. So the gamma 1, the projective transformation group acting on U1 corresponding E1, and then you can put this into a gray sphere disjoint from B1 because this is totally geodesic. And there is a convex domain in here where it acts co-compactly, but not necessarily freely. So let's say, change U1 to be the interior joint of this and V1, and then gamma 2 to be acting on U2 as a subgroup of cusp group. So the horospherical group will always be the cusp group. I mean, by cost group, I mean the ones also conjugate to these. So these are the standard cost group, I should say, right? And then you can embed this Sn minus I0 and Sai plus 1 in Sn so that they meet transversely at here. And then U2 can be embedded here, and then the gamma 2 can be embedded so that it fixes every point in this complementary space. And so U1 also here, and then gamma 1 acting on embedded U1, so that gamma x1 this space normalizing gamma 2 and acting on U1. So suppose you can do that. I mean, I don't really have any example to say, but right. Sorry, this should be +1. Like +1. Sorry. So you just say that there's some embedding homomorphism gamma 1 to normalizer of gamma 2 in OT Sn. Okay. So then this gamma 1 is a quotient like this, and gamma 2 is this, and then so then we find this automorphism zeta fixing on this element, and the Sni plus 1 as some unipotent element normalizing gamma 2, so that this corresponding matrix has only 2 norms of eigenvalue. So here it has 1 eigenvalue, and then here it has another eigenvalue, so it has only 2 eigenvalue. And then you want to make this centralize this group and normalize gamma 2. Okay, then so let U be the strict join of U1 and U2. So this will be properly convex domain, and then U mod this gamma and gamma 2 gives you an RPN diffeomorphic to sigma gamma 1 times sigma gamma sigma E1 times sigma E2 times S1 times R. And the transverse real projective orbifold is diffeomorphic to this, and so the result is called the generalized joint N, and the generalized joint N neighborhood, and so this is called the generalized joint group. Okay, so we can probably generalize this construction a little bit better. So by saying that gamma 1, gamma 2 are Lie groups, and they have some complex stabilizers and some parameter centralizing this and normalizing gamma 2, acting as a unipotent group here. And then you have to take the join, and then G be some constructed Lie group by taking the embeddings, and then you choose some kind of a discrete co-compact subgroup of G. So this will be more like the generalized version of the above one. Okay. Okay. Maybe I shouldn't say generalized here. Sorry, that's probably wrong. So I should only say generalized here, right? Okay. Right. Sorry about that. And so anyway, so some for the example is, so more specific example is like if you take the properly convex orbifold of dimension n minus I minus 1, 2, and so you find the map to the this group normalizing, and then you get this sequence, and suppose we want it to be split so that this act trivially on n. Okay, so let's look at that case. And let's look at n be one-dimensional, just generated by this group, okay, this element. And then if you look at these, so you look at the proximal semi-simple representation like this, acting on this cone. And then so look at these matrices, and you compute the inverse, you obtain something like this, and then you conjugate to get this. So so because of this form here, so these entries are all 0. So because of that, this means that A1, so this row has to be preserved under this action here. So this has to be some common eigenvector by these things. So so this means that there's some eigenvector of these group. Okay, so common fixed point, and so we can take any of something like this, and then this will because of this eigenvector condition, we can always assume that we can take these kind of things and construct these examples here, in our examples. But these will always have to be some sort of cone here, some cone over some groups here. So so now we want to discuss something about the hypothesis to get our main results. And so first of all, the look at the matrix form of the fundamental group. So I mean n holonomic group. Then these subspaces containing these, and they are preserved. So it has to be like this. And the final vector, these all have to be zero because B is a fixed point. So this corresponds to the BE here. And so SG is a matrix like this, and S1 and S2 are some vectors. So you call this part the upper left part. And so now we have some unipotent group acting on this space. And so of course these will be shown to exist later, but let's say these will look like this with so UG being the unipotent matrix and so on. And so let's define this kind of matrix where these are all diagonal, and then there's some thing like this. And these V are of course related, and then there's this norm here. And then these are some vectors here, depending only on V, this vector V. Okay. And these will be linear function. So up to here will be linear function up to I0. And so that so that this forms a group, you need these to be linear here, but not this one yet. But so we denote by C big C1 letter V to be the these matrix with this row from 1 to I0, and then the C2 to be the final one, this one here. Okay. And so lower left corner will be called the standard cost matrix form. So only this part, okay? So only this part, except this. And A hat will be the setting old identity, only setting this to be A, and then O hat will be these elements in the orthogonal group here of I0. So if you put this C1 and C2 to be all zero, then you call this standard cost group of type n plus 1 I0. And standard parabolic group is one multiplied by some possibly this orthogonal group. So these are called the standard cost group and standard parabolic group. So one's conjugate to these are. Okay. So the hypothesis 7.3.4 is that so we have this NK acting on K0 compactly and satisfy uniform transverse weak Miller eigenvalue condition, and elements are in this form, and N is in this form, and then this corner N is also in N, and this fundamental group normalizes N, and then the NX on this Pn fundamental group, Pn neighborhood, and this is always contains X on this intersection, and then this acts really faithfully on each dimensional leaves in this way. So of course I will later have to prove that this kind of thing exists up to some finite index subgroup and that kind of thing, right? And so if you look at the intersection with each of this neighborhood with this each leaf, then this will act transitively. Because this acts transitively, that it has to be an ellipse. Okay, so those are the thing. And so under this assumption, if it is u intersect HL prime, then it is actually an ellipse. Okay, so that's something to be proved. And the basic argument is that so you have to kind of look at all these elements, and because I did that only for so this is in certain coordinate system only, right? So and it's not yet normal. I mean the standard form yet. So the point is that you will have to now so you will have to kind of work with the change the coordinates to show that it is actually acting like a ellipse, the parabolic group here. And so I will skip that argument here. Okay. And so next lemma is concerns that so the orbit types are always going to be some ellipsoid, or it will be some singletons, or it will be not contain any properly convex domain. So if you have some group like this, okay. And so next is that so assume this under this hypothesis, then any element. So if you conjugate this element by NV by these elements, then you can always show that this is you because this is normalized, it will get to another element, but this is just V times mg, where mg is some kind of things like this, where OZ is in some compact Lie group. And this A5 is defined to be this A5 matrix, determinant, absolute value of determinant of A5 matrix. A5 is right, this matrix, so this is in the stand form, so this is the A5 matrix. Right. Right. Maybe I shouldn't say standard here, but anyway, so I think I don't know. But anyway, so keep continuing. So then we have this relation between A5Z square is A1 A9, or you have this relation. Okay. So this kind of shows that A1 A5 is same as A5 to A9. Okay, so they kind of have a same kind of relation between them, and these are all positive. And so basic proof is that you look at this kind of equation and try to relate B and B prime. So first you get this, and then second you get this, and then you have to compare the equations, and then you have this relation here. So 4-3 block of the first one is uh, is is this, and then a 4-3 block of this one, second one is this, and all right, so you can cancel these A8, and then you get A9Z, B is B prime A5Z. Okay, so that's how we get this, and the 3-2 block of the first one is this, then 3-2 block of this is this, so we obtain this. Uh, so what then I have to do some tricks that you choose some corner where S1Z is 0, because there's by Proud fixed point, there's a fixed point of any element in this K. K is a compact convex set, so this is a 4. And so this is a sort of bounded change of coordinate, and then the uh, and then under this assumption, so this is 0, then we get this relation, this VT. So this inverse is related to this VT in this coordinate, and so you have this relation. And of course, under this coordinate change, these constant doesn't really. I mean, these constants will change, uh, but these are all bounded sort of coordinate change, and then we form this kind of a matrix group, and this is for each G, and they are also orthogonal by under some corner system. Okay, so with a bounded sort of corner system, because for each G you can change, you can find this corner under some sort of bounded change. Okay, and then the thing is that if you have some group where each element is conjugate to an orthogonal group by uniformly bounded conjugating matrix, and G is actually a compact Lie group. Okay, so that's what I'm using here. So so that's how I prove this similarity theorem, and then next I show that K is actually a cone. So so K has to be a cone over some low one-dimensional low convex domain, and then we can actually find the coordinate where it's actually orthogonal. These O5s are actually orthogonal, and so on. So again, I skip these because the basic idea is that in the dual, of course, these things will have some sort of fixed point, and then um, I mean, because these act on this dual domain as some sort of orthogonal element. So orthogonal element will have a fixed point on if you act on some orthogonal group acts on some convex domain, then it'll have a fixed point. So that's how I get the common. So you get this hyperplane, and then you get have to have a cone. Okay. So again, these are much computation, and then so once I have that, then I have this get a cone, and then so once I have cone, then these are in this corner is actually 0. This will be, and then you can just get the this be the orthogonal group. And then on this hypothesis where and then NK acts semi-simply, then you can get for the nice equation, and the mu g is right. So the mu g was this. Uh, sorry, mu g was this relation here. Should go further. Right, mu g is this relation, and then I mean this ratio. And then if mu g is 1, then actually these are all same value, and then these are also just multiples of the lambda with e. Okay. Again, those are some computations, and so there are some more technical things that you can centralize some Cholesky dense set, and its mu g is 1, and so on. And this Aleph 7 is another constant. So when mu g is 0, then you divide A7 by the lambda VE, and then you remove this value. So this is the sort of how far it's different from the this cusp group. Okay, because here in the cusp group it has to be just lambda VE times this. So you're just looking at how different they are from that. And then you see that these are sort of linear, they satisfy this linear property. And so this is actually going to give you a map like this, a homomorphism to R. And you can kind of understand this mu-g by factoring like this group. So this part now looks like the cost group here. I mean some constant times the cost group, and then this is really sort of a translation in the VE direction. So you can see that this this is pushes things down in the VE direction. Okay, so that's the only thing that here. And then so the splitting is really that if you assume this hypothesis and this is strict join and if you have some commutant of the finite index group that is positive diagonalizable and is a abelian group rank I and so on, then uh, then actually you can find this sequence and you can actually embed this k double prime, which doesn't really exist, into this real Sn, actually the boundary about tilde, and then you can also find the corner where all these are zero. Okay, so the ones which I mean these entries are zero. Okay, so the way to do it is of course the using this centrality. You have to push map everything to the um, uh, so again, you use the largest eigenvalue of some elements in the center, and then you push everything to there, and then you see that be that has to realize k double prime because the central element will in k star will be realized above some element with the strongest eigenvalue there.